Hi, everybody. My name is Spencer Shanson. I'm head of architecture for Paramount Streaming. I'm here to talk about how you build out basically a fast linear streaming platform at scale. Or in other words, how to squeeze 10 years worth of experience into a 30-minute presentation. So this is going to be some stories with a few lessons. So cast your mind back. It's 2015. Pluto TV is an 18-month-old startup company. And it's trying to do something rather contrarian. At the time, everybody's trying to move on demand, provide video on demand. Pluto TV thinks there's still a market for viewers who watch linear content, curated programs on channels over the internet to connect to TV devices. So the company is about 18 months old. It's built out some core technologies for the first generation application. There's a few key in-house software components, which are basically a content management system or a CMS running on Mongo database. And it's got a number of main schemas data structures inside it. It's got the channel, of course, and the channel contains a scheduled list of VOD assets. It's basically a VOD playlist, perpetual VOD playlist. So every channel has a scheduled timeline. Inside the timeline, there's a reference to an episode. An episode has one or more video clips and 0 or more ad breaks. The video clip is basically a video on demand item that's sitting on a CDN server. So being a startup, Pluto TV wants to be everywhere, wants to have as much reach as possible. So they're supporting the app on web, on iOS, on Android, on Roku, some connected TV sets like Vizio. And all these implementations all have the same logic, replicated 5 times. They're all replicating playback logic. They're all working out how to request ads from the ad serving engines out on the market, using VAS, which is an industry standard XML-based template. I see a few smiles over there. VAS is video ad serving template. It's XML-based. It's difficult. It's gnarly. You get back a VAS response that says, I don't have an ad for you, but try this guy over here, who then says, try this guy over here. So they're all replicating the same logic. They're all replicating ad beacon firing logic. Ad beacons are the URLs you have to fire in order to tell the advertisers that the advert's been played so you can get paid. And they're all managing the time management and scheduling sequence. Great for a minimal viable product, but the user experience is actually pretty poor. The apps are all calling the ad servers at different times. There's buffering between the clips and the adverts and between adverts and clips. They're all drifting off schedule in different ways and have different algorithms to try and catch back up. So the leadership knows at the end of 2015 and beginning of 2016, they need to improve this. And they kick off a new project called the TV Experience, or TVXP project. And it has a few simple goals. One is to be able to generate a single continuous linear stream for every channel and have a TV-like experience. They want that consistent quality playback across all the platforms. And they also want to address one of the key complaints they're getting from their MVP viewers, which is that audio levels are all over the place. Different clips and all the adverts have different audio levels that people are constantly changing the volume. And if that's not difficult enough, they want to do all this in 3 months and replace the existing transcode vendor they're using because the contract's coming up. So of course we can do this. This is what we put together. This is the TVXP 1.0 project. Right in the middle there is this video playout system. It's what we call the stitching service. It's basically a manifest manipulator. It's written in Node.js, and it's generating HLS live manifest files for a video player and pointing that video player to the actual video content on CDNs. That video playout system, or the stitcher system, is data-driven. It's driven by the CMS. So it's reading the data out. It's making Mongo queries to read the data out of the database. And we pull the ad system out of the application, moves it into a new back-end service called an ad proxy, which is basically proxying all that vast logic and parsing the XML and returning a nice, clean JSON object to the stitching system. And then all the adverts, all the content is going through this new transcoding system where we're transcoding all the content to exactly the same video profile. So content and adverts all have the same video ladder. So why HLS? It's 2016, HLS is everywhere, Dash is coming on board, but it's not really deployed everywhere yet. And we're using 5-second segments because that's a good compromise between video quality and bit rate. And 5 happens to divide nicely into 15-second and 30-second adverts. And the Stitcher system is generating a 30-second sliding window, which means every 5 seconds, that video player is coming back and asking, what's the next 30 seconds look like? So one thing to know about HLS, especially for live HLS, is it is a state machine. Every stream is unique. So at the top here, we have the information that's in the CMS. And basically says, for this episode, for this episode, you have 2 clips with ad breaks at the end of each one. And given 2 separate viewers, 2 separate streams, they both see the same content, but one viewer may get 4 adverts, 4 15-second adverts in their ad break. Another one gets 2 30-second adverts in the ad break. And that means the media sequence and discontinuity sequence counters that are monotonically incrementing on the stream need to store the state for every single active stream, which leads us to make some architectural decisions. Given that we are replicating the same logic across all these different platforms, we want to make the platform as simple as possible and move as much logic as we can into the cloud. DVD, are you here? Yeah, there you go. Right. So put as much logic as we can into the cloud. We want to decouple the Stitcher's internal playlist representation, which we call stitchables, from the CMS. And we need to store this state somewhere. And we have an internal conversation. Should we make the sticky sessions so that every client, when a client calls a Stitcher, it's going to exactly the same instance, and you can store the state on the instance in memory? We decide that's going to be kind of brittle. We want to be able to scale up and down the Stitcher servers. So we decide to use a central Redis cache instead. Stitcher, we got clean separation of concerns. The Stitcher knows nothing about how ads are decided and fetched. That's all handled by the ad proxy, and the ad proxy services manages that vast protocol. So it didn't take 3 months. It took 6 months to build this from scratch, but we roll this out. It's the 1.0 TVXP platform. We start with a few channels. We see how they perform. It looks good. Over the next couple of weeks, we roll this out to all 40 or so channels that Pluto has available at the time. And what could possibly go wrong? It's working great, right? Well, scaling is fun. So with an improved viewing experience, we get more viewers. More viewers brings us more content and hardware partners, which brings us more channels and more creatives and thankfully more revenue. And in order to support this growing viewership, we have to add more servers to the pool. Each one of those servers, those stitching servers, is making the same request to Mongo directly. And as we're adding more servers and more channels and more content, each Stitcher server starts up more slowly, and it's putting a huge strain on that Mongo database. That Mongo is used by other services in the platform as well. They all depend on Mongo, and Stitcher is degrading the Mongo performance. If you look closely, you can see that there's these huge spikes in Mongo response time. Happens a few minutes before the top and bottom of every hour, because now we have more channels. Content turns over the top and bottom of the hour, and this is degrading the performance across the entire system. But that's not all. Because we now have more viewers, we now have more streams with state, which means there's more reads and writes to and from the Redis cluster, or the Redis database. And we only have one Redis node deployed at the moment to store the state. And if that ever gets overloaded, we've got nowhere to go. We've got no backup at this point. But it's okay. This is a 12-core CPU. We're using about 20% of the node's RAM. We're only using about 10% of the CPU bandwidth. I'm keeping my eye on this. I know there's nowhere else to go. So we've got plenty of headroom before we need to worry. Except one morning, I get a call from the engineers down in LA. I'm based in the Bay Area, telling me that the Stitcher is stalling, manifests aren't being generated correctly or quick enough, playback is stalling, our view experience is degraded. And I'm like, it's not the Stitcher. I got the numbers in front of me. It's looking pretty cool. And then I remember Redis only uses one of those 12 cores. And 10% of the total CPU has saturated that one core. And holy squirrels, what do? It turns out I get that call just as I'm getting on the train to go to San Francisco for demuxed. I'm not going to miss demuxed. I get on the train, and I become a Caltrain coding ninja. I now have to swap out that single Redis node with a new multi-sharded cluster in place with no downtime. So there's nothing like pressure on a train to help you write some code pretty quickly. And I'm writing it, I'm pushing it out to GitHub, while the guys down in LA are spinning up these extra nodes. And by midday, everything's calmed down. We got it working. Somehow we pulled that out. Okay, at this point, the company is growing. It's time to address those 1.0 shortcomings. We need Stitcher 2.0. We have to update the platform and engineering practices so we can scale the business. So we set out with some technical goals for this 2.0 project. First of all, we want to decouple that Stitcher from the Mongo databases. And we want to decompose the source clips into those internal stitchable representations just once for the whole cluster, instead of having every single one of those service instances doing it as well. We're getting new requirements from the ad systems. So we want to break apart the ad proxy monolith. We also want to insert adverts with frame accuracy. Remember, we got those 5-second segments, which means we can only insert the ads in the ad break at the end or the beginning of one of those 5-second segments, which could be mid-sentence. That's not a great user experience. It's one of the biggest complaints we're getting, along with the audio normalization we didn't get to in 1.0. Pluto TV is also getting some live sports at this point, so we need to support live streams with dynamic ad insertion. And we want to build out a feature we call flexible timelines. So given a scheduled, say, 90-second ad break, we can only fill sometimes maybe 60 seconds or 75 seconds with ads. And we've been padding those ad breaks out with Slate in order to keep the schedule. We now know, because these are virtual linear channels, we actually have the VOD assets on the CDN. We can collapse those ad breaks, remove the slate, and we call this flexible timelines. But we also notice that as the feature set is growing, the application is taking longer to launch, and so we need to be able to scale the APIs too. And as for our DevOps practices, we started with bash scripts, believe it or not. We then containerized all of our services, and we're running Docker on Amazon's ECS service. And we actually have some homegrown CloudFormation templates that are really gnarly, difficult to maintain. I'm kvetching about them all the time. If you don't know what that word means, look it up. And so I come up with this new project called Kvetch around Kubernetes, around Vault, and using Terraform and CI/CD over GitHub Actions, basically modernize our DevOps practices. So let's take a look at Bootstrap. Just like the Amiga, Lionel, I want the application to have just one entry point to kick things off. So we create this Bootstrap service whose main role is to generate a JSON object that gives the application as much information as possible, or all the information it needs to render that first frame on the screen as quickly as possible. We talk about it, and the back-end engineers realize that this is basically just going to be aggregating multiple API calls, and they're not sure if they can actually do this fast enough. So we established some SLIs and SLOs, service level indicator and service level objectives. The SLI we put in place is measuring the request response time. How much time does it take to generate that and push out that first byte of the response, the JSON response, from the moment it gets the request? And the SLO for that is going to be 250 milliseconds. So this is something that's measurable. It's something we can track. And we put the rule in place. And the engineers are actually confident they can meet this because we're rewriting a lot of our services from Node.js into Golang. So it's a win-win situation for everybody. We also noticed that as the platform is growing, as features are growing, there are more parameters about the user session that we're adding to all of our APIs. So every time we want to add a new parameter, we have to update multiple services with this new parameter before we can roll that feature out. So we decide that the Bootstrap service is going to encapsulate all this session information into a JavaScript Web Token, or a JOT. On the Stitcher side, we attack that Mongo problem. We decouple the Stitcher from Mongo by introducing this new service called the Active Content Service, which is basically a smart cron manager. If all the channels have timelines and all those timelines are scheduled, then the Active Content Server will know when the next timeline is going to start and when the current one is going to finish. So it basically sets up a timed event on every single channel that is published to say, like a few minutes before the end of the current timeline, reach into Mongo, find out what the next timeline is, pack all that data up, and fire it off to a Lambda function that's going to generate the stitchables for the Stitcher and put them in a new Redis cache that all the Stitcher services are going to read from instead of reading from Mongo. That Stitchables Lambda is using the same code, the same data structure that's private to the Stitcher service. So yes, David, it is in a mono repo. The video player and ad proxy are unaffected by this, and all the Stitcher has to do now is stop looking at query parameters and look at JOT parameters when it gets the request. As for the ad proxy service, the ad team, the engineering team is growing. We're adding more features. They want to be able to develop faster. So we break the ad proxy monolith up into a number of different microservices. One of those I'm going to talk about is the ad requester. So this is the refactored code from the original ad proxy service that's basically making the vast XML requests and handling the response and parsing it before it passes it off to other parts of the system. It's written in Node.js. Node is not very good for XML parsing. There are no I/O blocking calls when you're parsing XML, and on Node.js, that means the CPU becomes a choke point. So the team rewrites it in Golang and gets some benefits from that, because a lot of the other teams in the engineering organization are also using Golang. But they're kind of curious about Rust. How does Rust perform in this situation? So they do some experiments, and it turns out that Rust is an order of magnitude more performant, especially for XML parsing. But there's a problem. We're not a Rust shop. We were a Node.js shop. We've become a Golang shop. And there's some pushback on deploying this because we don't know how to observe Rust. We don't know how to monitor Rust. We don't know how to put Rust in our CI/CD processes. So the architecture team, engineering team, we come together with the ops team, and we collaborate, and we work out this. We need to become Rust. The numbers show that there's clearly an advantage to doing this. Let's make it happen. And then there's DRM. Because up until now, we have been DRM-free. Our content's actually encrypted because one of our content partners insists that our content is encrypted, but all of the keys are actually available to anybody, so there's no protection. And at this point, we want to get higher video quality content. We want to deliver at higher resolutions. So contractually, we have to insert DRM into the system. And this is a big project that touches almost the whole system. We have to build a secure key management system. We have to change our content ingestion system that pulls content in from our content partners to request keys from the KMS, pass it to the transcoder. The transcoder knows how to encrypt the content. We've also got to provide a secure key access to the video player using industry standard DRM protocols of Apple's Fairplay, Google's Widevine, Microsoft PlayReady. And if you want to use Widevine, you've got to use MPEG-, and we don't support it. So we can get HLS Fairplay out onto the market fairly quickly. And we're hosting the Fairplay servers ourselves. So that comes out, DRM for HLS on Apple devices with Fairplay, no problem. Getting Widevine out with MPEG- is a much bigger project, because we've got to teach the Stitcher how to generate an MPEG- manifest file. It takes the engineering team about 6 to 8 months, I think it does, to do Dash. Not so much the Dash itself, because generating the Dash XML file doesn't take that long, but working out the lowest common denominator or getting Dash working consistently across all the different Android platforms and other platforms that support Dash is a pain. We run into problems like, did you know that some platforms have trouble switching from DRM-protected content to unprotected creatives, adverts? We had to find that out the hard way. So now we're at DRM protecting our adverts as well, even though nobody's asking for it. But they work on this. They roll out Dash. They roll out Widevine. And shortly after rolling it out, something happens that's never happened before. Google Widevine service goes down. And we have no redundancy in the system for this. We learn our lesson. We actually look at what Paramount Plus did, because Paramount Plus was able to recover very quickly. Turns out they are using Adetto for their DRM handler, and Adetto uses Google Widevine, but they've also deployed Widevine themselves for backup. And so using Adetto, Paramount Plus was able to stay up while the rest of the Widevine system went down. So we learned that lesson, and what we do now, which isn't shown here, is we actually synchronize our key management system with Adetto with ours, and we can actually flip from one to the other if anything goes wrong. Polling. Polling also puts a strain on the system. Polling means we miss last-minute changes, like when Pluto was showing the Foo Fighters' Taylor Hawkins tribute concert, and it overran its schedule, and we had no way to change the schedule, and we cut off the end of the concert. Different systems are polling at different times. API servers are out of sync with their data. So I don't really like polling, especially when we know when we're publishing things ourselves. So we introduced Kafka to the system. And one of the first things we do with Kafka is pull out the active content service, which takes forever, doesn't it, Pavel? Yeah. And we change it for this data change processor. So every change that's happening in that Mongo CMS produces an event that gets put onto Kafka, and anything else in the system can react to that Kafka event. Our data change processors see when things are changing on the channels. It takes those changes, it passes the information over to the stitchable service that's generating those stitchables, and we now have an event-driven stitcher system. And what this picture shows here is where we went a little bit further, and for scaling and efficiency reasons, we've actually broken apart that stitcher monolith along two axes. One axis being the protocol type, HLS and Dash, and the other axis being the content type, VLL and VOD. So now we got 4 different implementations of the stitcher. We got 4 different stitchable Redis caches, because they all have their own traffic patterns, they all have their own different volumes of content. We're able to scale them up and down all independently. And that's all there is to it. Well, not quite. There's a lot of stories I didn't have time to cover. Things like, how we added support for true live linear streams, how IPv6 affects your advertising revenue rate. The night we DOSed ourselves, that was a long night. How we have to validate all these creatives using AI, there I said it, porting to GCP and so on. But, we never intended to build out this large, massive platform. What started off as a simple idea to deliver a TV-like experience over the internet evolved with success as requirements grew, as new opportunities arose with their own challenges, and we had to learn how to scale the system and our practices. Lots of lessons learned. Most of these are common sense, good engineering practices. Design for the future, think about what the future is going to be, but build for now. Know which metrics to monitor and monitor them, and know where your points of failure are. But a lot of the time, they're actually in things you can't control, like your third-party dependencies. Use loose coupling so you can modify your systems independently of each other. Maintain separation of concerns. Big, complicated systems are composed of lots of smaller, simple systems. And the one constant you're going to have, no matter what you're building, is change. Change is always going to happen. Systems evolve. New technologies like Rust come out that you want to adopt. So be flexible to that. Scaling is fun. And most of all, collaborate and communicate with your peers. So I'm going to leave you with a few statistics here. What started off as 40 VLL channels is now 3,000 VLL channels across North America, LATAM, and Europe, all using the same basic technology and algorithms that we developed 10 years ago. We've now got about 500,000 VOD assets available in production. We've optimized the Stitcher system down to about 2,500 Kubernetes pods across 8 namespaces. And the ad proxy has been optimized down to about 700 pods across 11 namespaces. What else can I say? Stitcher service, I'm actually embarrassed to say this, seeing as the numbers we saw from Netflix earlier, but we're up to about 20 million requests per minute. We're filling about 200,000 ad pods every minute. We're transcoding about 20,000 new creatives every day in under 5 seconds each, and we're using AI to validate and inspect about 40,000 different adverts every single day. And we did all this with no scheduled downtime ever. All right, thank you.